So, hello, welcome to day 15 of Advent of Code in Done and Go. You might have noticed that today this is coming out much later than the usual time. I said in yesterday's stream that today, because I was traveling across the country, I wouldn't be able to stream it at the usual time. And so now I've discovered that just with the way that things are happening in my new location, unfortunately, I won't be able to stream these live anymore. That said, I'm still going to do all of them. It's just that the videos are going to go up a bit later than usual. I also won't be going for the leaderboard anymore because I'm going to be hours behind the release of the puzzles. But I'm still going to do them, still going to have fun. So let's head into today's challenge and see what's up. Day 15, chitin. You've almost reached the exit of the cave, but the walls are getting closer together. Your submarine can barely still fit though. The main problem is that the walls of the cave are covered in chitins, and it would be best not to bump any of them. The cavern is large, but has a very low ceiling, restricting your motion to 2 dimensions. The shape of the cavern resembles a square. A quick scan of chitin density produces a map of risk level throughout the cave. Your puzzle input, for example, this. You start in the top left position, your destination is the bottom right position, and you cannot move diagonally. The number at each position is its risk level. To determine the total risk of an entire path, add up the risk levels of each position you enter. Okay, enter. That is, don't count the risk level of your starting position unless you enter it. Leaving it adds no risk to your total. Your goal is to find a path with the lowest risk, total risk. In this example, a path with the lowest total risk is highlighted here. The total risk of this path is 40 because the starting position is never entered. I'm just going to assume that's true. What is the lowest total risk of any path from the top left to the bottom right? Okay, let's check our input. All right, nice and big. Let's see. The first thing I notice when I look at this is that in the example, the numbers, the path only goes down and to the right. So my first question is that true? Can the path only head towards the destination? Because if it can, that makes it a lot easier to write an algorithm for. And I don't think that it can, because I can think of a path where you have like something like this, right? And if, let's say, all of these spaces were 9s, like this, then clearly this path is shorter than any of the other paths. The path going through the 1s. And that path going through the 1s does indeed double back. I wonder if we can treat it as a graph where each grid cell is a node, and then use one of the graph algorithms to find the minimum distance. Yeah, Dijkstra's algorithm, maybe it's called. Okay, I need to look this up because I don't know it by heart. Dijkstra's algorithm is an algorithm finding the shortest path between nodes in a graph. So, okay. Found the shortest path between two given nodes. Okay, so that sounds like something we could use, right? If we turn this into a graph where the weight going from this cell to this cell is 1, the weight from this cell to this cell is 6, but from this cell back to this cell is 1. And then if we said, let's take a look, algorithm. Okay, I think we can do it like this. I think we can do it like this. I have a question in Go. Can structs like this be used in a map like this? Data declared but not used. Great. There we go, now it's used. Okay, we can do that. Okay, mark all nodes as unvisited. Create a set of all unvisited nodes called unvisited set. Assign every node a tentative distance value. Set it to 0 for our initial node and infinity for all other nodes. Set it to 0 for our initial node. And infinity for all our other nodes. Okay, so we need to create our other nodes first. Let's say, I think we can keep it as a grid. I think we can keep it as a grid. I've typed this line of code so many times. During this month of doing this challenge. Let me write the data in. I think the data is, okay, we can probably do some low-level tricks to make this work out. So for each character in the data, we want to write that value as a number, as an int, right? So we minus this, I think. Typecasting. Okay, let's just double check that real quick. The final line starts 1456, 1456, and it finishes 8896. It finishes 8896. Okay, so we have passed it into a grid. We have a point struct. We have unvisited. So for let's see, max y is len grid and max x is len grid 0. For y equals 0, y less than max y. For x equals 0, x less than max x. If x is 0 and y is 0, we want to do this. Else we want to do this. Okay, so it's 100 by 100, and we have the setup that the algorithm said. Okay, what's next? It's been more than 10 years since I've gone through uni, and I have never had to implement Dijkstra's algorithm since then. So I do need a little bit of help. I could read the pseudocode one, but that feels, for me personally, I think reading a description of the algorithm and then actually learning and understanding how it works, that feels like a meaningful endeavor. Whereas if I read pseudocode and I just kind of translated it without really understanding it into code, then it feels like it's not quite as meaningful. So for me, this isn't really cheating. This is, I'm learning as I go, and I'm actually learning how the algorithm works, and then I'm implementing it off of that understanding, which for me, yeah, is how I like to do things. So for the current node, consider all its unvisited neighbors and calculate their tentative distances through the current node. Compare the newly calculated distance. Okay, so I need to keep track of tentative distances for each node. Right, which is why I made this in the first place. That's okay. I just realized the runtime of my algorithm. Like you need some kind of like a heap data structure or something to make this fast. But well, maybe there are other ways to do this. Maybe not. Compare the new. Okay. For the current node, so we need a current node anyway. Current is going to be 0.00. Don't know why it doesn't. Okay. Oh, it treated it as something. Okay. Consider all its neighbors. I'm gonna do it. I need a neighbors function. Which needs max x and max y. Okay, so if p dot x is greater than 0, we append out the point p dot x minus 1, p dot y. If p dot x is less than max x minus 1, then we do plus. Then we do the same thing with y. That should be good. Type point needs to be available for everyone to use. We'll keep them lowercase, it's fine. I'm just passing max x, max y like around like this because, yeah, I can't make it work. So let me just do this, see that that gives us 2 points as well, good. And something in the middle should give us 4 points. Good, and something like 0, 1 should give us 3 points. Good. Okay, so neighbors function works. Calculate the tentative distances through the current node. Right, okay. So unvisited. I can't keep track of it in unvisited. So this can't be unvisited. This is distance. Every node starts off as unvisited. Yeah. Every node starts off as unvisited. Okay. So we'll call it visited and not unvisited. Right, doesn't that mean every point is unvisited to begin with? That should be false. Cool. Yeah, so we don't even need to, because 0 values, finally, go, being useful. Okay. For the current node, consider all of its unvisited neighbors, calculate the tentative distances through the current node. Through the current node. So distance of the current node for each neighbor. For each neighbor in neighbors of current, max x, max y. New distance equals distance of the current node plus the cell we're trying to get to, which is grid n dot y, n dot x. Okay, if b was previously marked with a greater distance than 8, here, then change it to 8, otherwise the current value is kept. If new distance is less than distance of the neighbor n, distance of the neighbor n equals new distance. Okay, so okay, I think that makes sense. When we're done visiting all, considering all unvisited neighbors. Oh, all unvisited neighbors. If visited n, continue. Mark the, okay, so number 4, so step 4, when we are done considering all unvisited neighbors of the current node, mark the current node as visited. And remove it from the unvisited set, right? A visited node is never checked again. Right, that's why we have this continue. If the destination node has been marked visited, okay. If visited 0.9999, well, we'll do it properly, max x minus 1, max y minus 1. then stop. We are done. So we should just print out distance 2. That final node. Otherwise, we set a new current. So while we'll just do a while loop, like a while true loop. And break, right? Yeah. Otherwise, we have to set current is the node with the smallest tentative distance. Okay. This should be nil. We'll use 100, 100 to know, so which will cause an error if we manage to not set it. So there's no way to do this but to check every thing in distance. So for point value in distance, if value is less than min_dist equals value, min point equals point. Cool. Then here we can say current equals min point. So we can actually do it like this, right? We can just reuse current directly. Okay. That is the algorithm. And it kind of makes sense. It rings a bell, but I'm not 100% sure this is right. I'm going to run it on the test data because they give us the answer to it. And it is not finishing. I have missed a step somewhere. Okay, well, we can test this quite easily just by printing out what the current thing is. Then we'll see what's happening. It's always staying on the 0th point. Why? Okay, because we are trying to visit the 0th node again because it's always the smallest. If visited, if not visited p and how is it possible that so it sets current to 2, 1. That needs to go outside because otherwise, if all its neighbors have already been checked, then it gets stuck and it stays in unvisited. Okay. I think that was kind of anticlimactic. Climactic. It just spat up 40 and it was done. but the answer is 40. So, okay, so that was a little disappointing when you implement the algorithm. I kind of half take back what I said earlier about implementing the algorithm. It's taking a lot longer with the 100 by 100, but it spits out a number, 613. And it was right, so we keep going. 25 minutes, dang, that was hard. Okay, so I guess since I'm not doing this, doing this fast, doing this for speed, I guess the insight there was that that grid, you could treat the grid as a graph where each cell is a node, and the edges, the weights of the edges are just the values of each cell that you go into. And then using Dijkstra's algorithm, you can find the shortest distance between 2 points, which in this case was top left and bottom right. Now that you know how to find low risk paths in the cave, you can try to find your way out. The entire cave is actually 5 times larger in both dimensions than you thought. The area you originally scanned is just one tile in a 5 by 5 tile area that forms the full map. Your original map tile repeats to the right and downwards. Each time the tile repeats to the right or downward, all of its risk levels are 1 higher than the tile immediately up or left of it. However, risk levels above 9 wrap back around to 1. So, if your original map had some position with a risk level of 8, then the same position on each of the 25 total tiles would be as follows. Okay, I kind of get that. As it repeats across and down, you kind of roll the value around. Here is the full 5 times as large version of the first example above, with the original map in the top left corner highlighted. I think we can make this work as long as I have an efficient data structure for this. This is where a lot of the slowdown is happening right now, because I have to loop over all, in this case, 100 by 100, which is 10,000 values. And if we multiply it out to 500 by 500, that's 250000, which is 250,000 values. Like that is adding a linear step. Linear step, big of n step to my algorithm. But you'll notice that, see, this here is constant time. This is constant time. So, but this is linear time. So as long as I have a better data structure for this, for finding the value, the minimum distance, I should be okay. How can I, so I said a heap earlier, I think. But I don't want to implement a heap. Or priority queue or anything like that, which is implemented with a heap anyway, I think. Equipped with the full map, you can now find a path from top left to one right with the lowest total risk. The total risk of this path is 315. So 2 things important here. One is, how do we multiply the map out? That in itself is a little sketchy. And the second thing is reducing the runtime of this algorithm. Let's tackle the first one first, which is reducing the runtime of this algorithm. I mean, it has to be a heap, but I can't implement a heap in Go. I should just find one. found an example. Yeah. Implementation of min heap, implementation of max heap. I can think of a really not so nice way to do it. Maybe I should just use a min heap. I guess this isn't fully cheating because this sort of data structure, if you use something like Java, it would come built in, right? Except this heap. This is an int heap. And yeah, I can't, it's too hard. What do people usually use? This is an array that contains the current distances from source to other vertices. The previous array contains pointers, etc. Vertex and queue with min dist. It's just hidden in here. The simplest version of lectures algorithm stores the vertex set queue as a linked list or array and edges as JSON matrices. In this case, extract minimum is simply a linear search through all vertices. It's a linear search. Exactly. It's a linear search, and we don't want it to be a linear search. Maybe if I get rid of this print, I just want to see how long this takes. If I get rid of this print, does it go any faster? It doesn't. The print doesn't really affect it. That took forever. That was 7 seconds. It would take 25 times longer. But you know what? 25 times longer than 7 seconds is only something like 2.5 minutes. I can't wait that long. it'll be faster than me implementing something anyway. So I just need to be able to implement this graph grid multiplying thing. Cool. So first things first, we need to do this. We're going to use the small graph first. Max x and max y is now going to be 5 times these numbers. So times 5 times 5. That should run into problems on line 66, which is where we index into the grid. So instead of indexing into the grid, we need a way to do this looping thing. To do this looping thing, we have to go the number plus 1. Okay, yep. N dot y. Okay, y is going to be n dot y mod lane grid. And then we say y plus equals, y is going to be that, x is going to be n dot x mod len grid 0. So val equals grid y x. But now depending on we add 1, we add plus equals n dot y divided by 10 by len grid plus n dot y divided by x divided by len grid 0. If val is greater than 9, val minus equals, so if it's 10, it becomes 1, minus equals 9 plus val. 315. 315. Okay, so this can then do with a little bit of explanation here. But as I'm doing that, I'm going to set this off to run on my data because it's going to take a while. Oh, it's going to take a long time. Because that needs to get to 499499, and at the moment it's only at 30. I think we can speed it up actually. Just gonna not have everything in the array to start with. wait, if it doesn't exist in the array, in the distance, then distance n equals new distance. Else, if new distance is less than the existing value, then it's also that. And what we also do is we get rid of this, but we keep this. So this should zoom through the first bunch quite quickly, and it will slowly filter through the rest of them. Let me just double check that that actually works before I run it on my actual data. Cool, 315. Okay, let's go. So let me explain what I did here. So this is basically doing the task of multiplying the grid out 5 times without actually multiplying out the grid 5 times. Using the modulo operator, we are limiting, we're getting the value out of the original grid, which only exists in the smaller space, right? And then from that smaller space, so we have that. And then what this adding does is, for every 10 values, or every whatever number of values you move over by 1, this increases by 1, right? And then the next set time it reads, it increases by 1 again. And so if I divide by the length of the grid, so say my value is 14, right? My grid is only 0 to 10, but my y value is 14. I get the value at 14 mod 10, which is 4. So I get the value at the fourth, on the 4th row, or the index 4 row. So let's say it's the 7. Then because it's 14, 14 divided by 10 in integer division is 1. So it adds 1 to it, which is what this 8 is. And then here we just bound it and say if it's greater than 9, we loop it back. And to loop it back, we just minus 9, right? Because 10 becomes 1, 11 becomes 2, 12 becomes 3, and so on. And you just work out that that is minus 9. So the next thing I did with this distance thing is, before the first time, I was following the algorithm as it dictated, which was to assign infinity to all of the nodes. So I actually wrote it, max it, which is essentially infinity, into this. But what that meant was that every time we got to here to search for the next smallest node, we had to loop over 200 in the actual thing, 250,000 values. So what I did was, instead of doing that, I just didn't initialize it, and I said if it doesn't exist in the array, then the value is infinity, which means you just assign the distance to it. Now this doesn't actually solve my linear runtime problem, because, or quadratic-ish runtime problem, because even with this optimization, it is only a constant time speed up. I end up doing half the amount of work I would have done if I did it, or maybe a square root, probably half the amount of work that I would have done. So that's still running in linear time, but hopefully this will finish. So this is at 280. We have to reach all the way to 500. Maybe I do need, I'm not going to re-implement this. So I think what I'm going to do is I'm just going to let this run. You'll have to, I'm going to end the video soon. I'm just going to muse a little bit, and then let this run for the next however long, hour or so, until it spits out an answer and put that in. But yeah, it's also too late. It's just hit midnight, and my brain isn't working anymore, and I can't do any more programming tonight, unfortunately. I drove for 7 hours today, so my brain is very dead. I think this was a very instructive problem. It's about identifying the data structure, the algorithm. Someone who's just come out of comp sci, uni, or is interested in doing these things, or is using a language with the tools, the right tools to run these sorts of algorithms, I should be able to do this really fast. I am unfortunately out of practice, so I had to look it up. But yeah, I think with the right, I think this is the most important takeaway. There is so much research into these core fundamental algorithms in in computer science. And sometimes I think we, as software engineers who are usually doing higher level things, right, putting out applications together, pulling together web services and things like that, we neglect to keep ourselves up to scratch with these fundamentals. And we all kind of know that they exist. We all kind of know that they are there and that we can use them. But the reality is we very rarely have to actually use them. And so then this is like pulling out that dusty thing out of the corner of your cupboard and making it work. Um, yeah, this highlights another problem in Go with the lack of its higher level data structures, right? Because without generics, um, how do I implement a priority queue without re-implementing the entire priority queue or a heap or whatever other thing I need in order to do this? Um, I just don't have it on hand, and that is a problem, I think. You can't implement everything from scratch every time. Um, yeah, so I'm gonna call it here. Gonna let it run and put the answer in to get my star. Um, but yeah, so hope the video isn't going to be too long, and have a good rest of your day wherever you are in the world. Thank you for watching, and I will see you again tomorrow.